Hey YouTube, Tire Metalhead Weatherman here. Hopefully you guys are doing well. In this one, we're going to be talking about a little something different. We're going to start to look a little bit more towards the winter weather side of things. I don't know why my computer's updating, by the way. But today we're going to talk about something that's pretty prevalent, and I'm pretty sure a few of you had a question about. And that's regarding these lines right here. What are these lines? What do they mean? Why are they so significant? Why do you keep talking about 540 line, huh? So, to put it in perspective, these are called constant pressure lines. These are measured at different levels of the atmosphere. For example, 500 millibars to 1,000 millibars on this map. And this is the preset map that a lot of you are more familiar with than some of the others. But these indicate temperature, wind speed, and in some cases even humidity. But figuring out how to read the shaded contour charts is going to be a story for a different day. So let's start out by figuring out just what exactly these millibar pressures mean exactly. So probably the most important pressure to start out with, and this is my favorite pressure to look at because this is where you find those shortwave troughs in those big storm systems, and you can kind of gauge out how strong they are just based off of the 500 millibar level. 500 millibar level is an area that ranges in the elevation between 16,000 to 20,000 feet. So basically 4,980 meters all the way to 6,000 meters. It's considered the middle of the atmosphere, so we're looking about 15 plus miles high, so to speak, 15 odd miles or so. So why is this important, right? And what does it have to do with the lines? So for the 500 millibar level of constant pressure, the last digit in there, like say we were looking at this, 6,000 meters, for example, the last digit 0 is removed. So in other words, when we see 6,000 meters, we'll just see 600 millibars. So the actual height, whenever we see that 600, is going to be 20,000 feet. Usually that's going to be indicative of warm air as warm air rises and cold air tends to sink. And when we see something like a 564, that's about 18,000 feet. This is also indicative of warmer air. The colder the air is, like say 4,980 meters, we take that 0 away, that's 498. That's well below the 532 line. That's below freezing, and most likely, if I remember correctly, probably below 0. So that's a general idea of how the height contours work. Another way to look at things is vorticity. On vorticity, and you guys, if you've watched enough of my videos, especially when it comes to severe weather, you know that vorticity map is my favorite map. It's not only relevant with severe weather, but also winter weather too. So I'm often looking at this map first on almost every video that I do that talks about a storm system. So that being said, when we look downstream ahead of areas of maximum vorticity, we'll end up seeing those darker colors. I might try to see if I could sneak in a little clip off to the side here to kind of display what I'm talking about. If I can't, then I'll just try and do like a screenshot that kind of goes over that in a post. But that being said, we can also look at stuff like humidity through the 500 millibar range, but that's a contour map, and that's honestly another video in and of itself. I don't want to make an hour-long video for you guys because obviously watching a 20-minute video is sometimes hard enough as it is. So that being said, we look at this map here for an example, and we can clearly see here that we have our 570 line here, which is pretty daggone warm. Or actually that's 576. I couldn't really tell. I'd have to zoom in a little bit more. But 576 line, which is about 5,760, 5,700, so on and so forth. Here's our 540 line right here, which is 5,400 meters. The lower that meter level drops, the colder the air tends to get. So when you start seeing stuff like 510, which is like all the way up here, all the way towards the northeast, for example, that's how you know it's pretty daggone cold. So that's how we read the 500 millibar range. We go to the 700 millibar range. It's a pretty similar deal. So a height value of 282 represents the 700 millibar elevation of 2,820 meters or 2,820 meters, whichever one you prefer to hear. Now at 700 millibars, the number, of course, is going to be a lot lower, but this isn't really going to be as relevant in regards to temperature. We can look at stuff like relative humidity on here as well. We can look at the omegas, and that's, like I said, that's going to be another video in and of itself. You can see our wind barbs, etc. Mid-levels, I don't really look at that too much because there's not too much that goes on differently between these two levels of the atmosphere most of the time. However, just like with that ice storm that occurred over this last week, every once in a while the 700 millibar region influences a lot of things still, and that was a perfect example. So let's go ahead and drop all the way down to the 850 millibar range. Very crucial range. This is where you look at stuff like the low level jet, and this is great for looking towards wind, and this is a critical point when it comes to precipitation forecast because we're starting to get very close to the surface. This is very often how we end up seeing stuff like Cape value, so to speak. And of course, just like with the last two, 0 is omitted in this case. So if we see something like a height value of 132, this represents 1,320 meters or 1,320 meters. So one thing to look at here that's unique to this map is we can look at what's called precipitable water values, which is a measure of the depth of liquid water at the surface that will result after precipitating all the water vapor in a given spot. So, all right, so we look here. When we see a value like 156, for example, that's a pretty decent value, so to speak. And then we can look at, and then the precipitable water values are usually measured in inches, something we're very familiar with. And then on top of that, we can also look at higher Cape values with higher precipitable water. They can produce increased amounts of lightning, flash flooding, etc. So here's a look at precipitable water values, and they fall right into these little contour lines just as so. The higher values are going to be indicated in the green. Lower values are kind of indicated more so in the yellow. Again, we'll get into further detail with this in a later video because we could end up making this like an hour-long video when it really doesn't need to be. All right, so the last thing to look at here as far as this is concerned is the thickness chart. So looking at constant pressure charts, the thickness, this is what we see here. And it's even indicated up here on this part of the screen. 1,000 to 500 millibar thickness chart. And this is a shade, and this is a mostly shaded color here. So whenever we start to see fronts, a good indicator of what's going on here is you'll see those red and blue lines getting closer and closer to each other. And there's no really hard and fast rule for determining fronts using the thickness color or a thickness contour, but more often than not, this is the most uniform way of seeing it, is whenever we start seeing these lines getting ever closer to each other. This is indicative of stronger wind speeds, a lot of forcing in the atmosphere at times even, and also just an intense temperature gradient. So 540 line, this is why it's important. Traditional line to determine rain versus snow. 540 line closely covers the 32-degree point. So if precipitation is expected for locations just a little bit behind that 540 line, more often than not, we'll see some type of frozen precipitation. More often than not, it will be snow, but depending on what happens in the mid levels of the atmosphere or low levels of the atmosphere, we could end up getting sleet, freezing rain, etc. So anything past that 540 line, of course, we're more likely to expect rain. Of course, pending the low and mid levels of the atmosphere. Now, another thing to note here is gustiness of wind, and that's where these black contour lines come into play here. So the tighter the tighter in these lines are together, the stronger the wind speed tends to be. And I've mentioned that in a few of the videos on here, especially in regards to severe weather. Same applies with winter weather. So this indicator right here doesn't show extremely strong wind speeds. It shows minute wind speed. There's no real determining method to use these lines to determine exact wind speed. So let's not get into that. Let's not go in here thinking that. But excuse me. But if we were to put these isobars to the surface here, then we start seeing, let me get these isobars out, a couple of those isobars out. So here's where our upper level temperatures are. Here, our surface, here's our thickness temperatures here, and then right here are our isobars. I'm going to move this out the way. And these are where you start to see those stronger wind speeds coming in when we get like this little pressure over here, for example. The tighter these lines are, the stronger the wind speeds are. And one thing I also like to note is this is a little different when it comes to stuff like severe weather. If you want to get more info on that, I will post that video in the top right corner here, because understanding levels of forcing are going to be extremely important when it comes to tornado genesis in particular and supercellular storms. So now that we've seen we've seen what that looks like, we'll go ahead and actually apply that here. We'll take a look at what's going on over the country right about this time. I'm thinking the OOZ run probably should be coming in soon. Most likely it hasn't yet. Probably got another hour or so to go. Nope. Okay. So this is what we have to work with here. Let's go ahead and take a look at the country as a whole right now. It's not really a big low pressure area coming in, but you can see where these lines are moving. Here's where our warm air is moving, and here's where our cold air is moving. If those lines draw closer together, that's what we're seeing, an intense temperature gradient. It's more prevalent over here, where you could see this snow developing over here towards the mountainous ranges of the west here, especially towards the Rockies. And right where this 540 line is and this moisture has occurred, you can see this is indicated as snow in the blue. Here's the legend down here at the bottom. And then right over here, here's our low pressure that's offshore at this point. But you can see those little wind gradient, those little tight isobars right here. This is indicative of our wind. The closer we are to that low pressure, the stronger the wind gets. So as a result, you see these tight wind gradients over here. It's 1,000 millibar low pressure system. Pretty strong, but not going to be effective for anyone. But we'll see this move off, and we'll see those lines become tighter as this storm strengthens. So we'll watch this move out, and then we'll watch the next system come in. A little bit stronger winds developing here, but nothing too out of sorts here. Could this influence lake effect snow? Big question. Kind of leaning a little bit more towards no at that point of time, but we'll see what happens next with that. But that's pretty much how that works. Now the next thing I'm going to go over here, and this is how we'll close out the video, is I'm going to go over this right here. What in the world does this mean? I'm betting some of you have asked before. What does the Z mean here? That's universal time. So what is universal time then? I'm going to show you. So, simply put, universal time was created in 1852. This is a history lesson, by the way. Now, yeah, that's what we're doing. But the origin of the time zones began in the 1800s in England. Royal Observatory in Greenwich, England, began transmitting time telegraphically, and in other words, that's how time zones ended up being created. So UTC is basically universal time, and the Z is the Zulu in terms stemming from military usage, while coordinated universal time is a civilian term for the 24-hour clock. So that's where the origin of the Z comes from. And basically how this will work, the time zones are offset as follows. We have time zones ranging as far out as 12 hours behind Universal Standard Time all the way up to time zones that are 12 hours ahead of Universal Time, of Universal Coordinated or Coordinated Universal Time. And I wonder if I just said Universal Standard Time or whatever. Jeez, you know what I meant. Anyway, so the 24-hour clock or Z time begins at midnight at this point, prime meridian. So for OOZ for the US, for example, and we'll see this here, like let's say Eastern time, if I show OOZ on this clock right here, I'm going to move this back actually. Uh-oh, wrong button. But okay, so we're looking at Tuesday OOZ. That in Eastern time, that would be 7 p.m. I just clicked the wrong window again. So in standard time, Eastern time is 5 hours behind the Z time here. Central time is about 6 hours behind that. So if you're looking at OOZ, you basically just subtract 12 from 6 and you have 6 p.m. 7 hours from Mountain time, that's so basically you minus 12 from 7 and you get 5. It's pretty simple when you actually think about it, but it's just I think it just throws a lot of people off. It threw me off at first too, so if you felt like you were silly for not knowing, don't. I mean, it's pretty common actually. But yes, this goes so on and so forth, like Guam and Hawaii, their time differences are pretty interesting. For example, Hawaii is 10 hours behind Universal Standard Time, whereas Guam is 10 hours ahead of Universal Standard. And just for good measure, here's the Daylight Saving Time version, or the Daylight Savings Times version. So basically EDT, CDT, etc. So basically you subtract an additional hour. So OOZ for the Eastern Seaboard, EDT, basically that's 8 p.m. Central 7, 6, 5, 4, etc. But yeah, it's pretty simple. And if you want, I can actually, and if you guys would like, I would actually go ahead and screenshot these and put them on a post here and keep that up so that way you guys have a point of reference. But either way, I hope you guys found this video useful, especially to my fellow weather nerds. Wasn't a pro at explaining everything on this one here. If it was a little off, I do apologize. I may remake this in the future, just depending on how things evolve here. But that being said, if you did enjoy it, if you did find it useful, you know what to do. Hit the like button. If you haven't subscribed already, then do the double click. Give me the like and the subscribe. Always appreciate you guys for being here. Appreciate the growth in the audience from last month. Thank you guys a bunch. Goal is still to get to 300 subs by March, which would be the 1 year anniversary of my first video being up. I think it was March 6th to be exact. Either way, appreciate you guys being here. Much love. This has been Tire Metalhead Weatherman. I'll see you guys in the next video, which will be really soon. So take care until then.